Hello, everybody from Dr. Harshman's classical mechanics class at American University, or just any generally interested science people around the world on YouTube. I will be talking about the gradient. Now, basically, the gradient, if we're talking about a scalar field, gradient is a vector field which is going to, at any given point, model where the slope is going to be the steepest. And I'm a little new at doing these things, so just bear with me. It requires the del operator, which basically involves taking the partial derivatives. So let's say we've got called this del f, gradient of f. F, let's make it a Cartesian field in x, y, and z. That's the case, then our general equation for the gradient is going to be partial with respect to x in the x direction. I use I, j, and k for the unit vectors. Dr. Harshman likes to use x hat, y hat, z hats. You know, it's basically the same thing. I'm a math major, so I do things a little more crudely. Anyway, take the partial with respect to each variable in the direction of that variable. And in general, the gradient is very useful. And anytime we're doing some big calculations with a vector, it's got a lot of uses in calculus, differential equations. I had a professor last year, Dr. Casey, loved to say the gradient is your friend. It makes your life a whole lot easier when you're doing more complex problems. The gradient is your friend, and the Jacobian matrix is your friend, not to get too far off topic. And then the gradient, it can be generalized to things like gradient dot f. You dot it with a force field, and that'll give you the the div, the divergence. Basically a measure of the rate of outward flux from the center point. You also have the gradient cross f. That'll give you the curl. And that's rate of rotation, measure of rotation, basically. Anyways, let's get back to the gradient. In the past homework, there was a problem that involved doing gradients for some given scalar field, so let's do a few of those. The first one was x squared plus z cubed. Now, for the first part of it, you want to take the partial with respect to x, so just leaving z constant, just simple power rule. 2xi. And then there's no y terms. That's easy. Everything just goes to 0. I'll put 0j just so you can follow. And then finally with, you take the partial with respect to z, x term goes away, you get three z squared k. Can also be written, in a really, crude form: 2x 0 3z squared. That's just me, the math major, doing things really crudely. Anyways, okay. Starting to get it now? Alright. Another one they gave was f equals ky, where k being our arbitrary constant. Okay, of course there's no x in the first one, so the first term's pretty easy. 0i. And a linear term, you just knock off the variable, you take the coefficient, so k, j, and then no z term, so k. Oh, there's two k's, so I'm just gonna put hats over them to distinguish. Alrighty, okay. Alright, next one they gave was f equals r, where r is in the scope of spherical coordinates. Now, just to do this in spherical coordinates would be really easy, because since r, theta, and phi are always going to be perpendicular to each other, you can do this just the same way as Cartesian coordinates. This spherical would just be 1, 0, 0, just taking the partial respect to r. And that's easy. But if you wanted to do it in Cartesian coordinates, you got to remember the whole Pythagorean theorem that r equals square root of x squared plus y squared plus z squared. Looks like kind of a beast to derive, but you change this to a 1/2 power, and then remember the chain rule. Subtract 1 from 1/2, it becomes a negative 1/2, or a 1/2 in the denominator. And then for each variable you take in the partial of. Derive that, so 2x, 2y, 2z. So a gradient would look sort of like this. Okay, and if you did the deriving correctly, you get the 1/2 out in front, as per the power rule, and then you derive each term. You get 2x, 2y, 2z, and the 2's of course cancel out, so you get